Okay, hi everybody. Thanks for coming to my talk. My name is Woli Pereira. I'm a researcher at the Alan Turing Institute, and this is joint work with colleagues from University of Bristol and University of Kent. So what we're interested in is what you could call provenance-aware data visualization. To understand a visualization, we need to understand what the visual elements actually represent. At minimum, this involves understanding the data that they're computed from. So we have captions that help, but captions are only comments. They don't have any semantics. So what developers sometimes do is implement features like this. When the user moves their mouse over a visual element, like this small dot here, a view pops up with a summary of the data relevant to that element. This is super useful, but it takes a lot of programming effort. It also involves anticipating all the things that the user might be interested in. So our research question is whether we can use techniques from program analysis and data provenance to do this kind of thing in a more automated and universal way. So there are two use cases that we're interested in. The first is something called brushing and linking. So brushing and linking is a popular comprehension aid from the data visualization literature, and it helps users understand the relationships between different views of the same data. However, existing implementations of brushing and linking are ad hoc and quite limited. We want to automate it and do it in a mathematically robust way. The second use case is about allowing a user to interactively explore input-output relationships in a similar kind of way, but perhaps between two stages of a computational pipeline. For example, to help them understand an algorithm. So I'm going to illustrate each of these use cases now with a short demo. The demos are pre-recorded because our current implementation is quite slow. So in the first demo, we have a couple of charts. That we want to understand. On the left, we have a bar chart showing some kind of aggregated quantity, and on the right, we have a line plot showing some time series. And the idea is that as we select visual elements, the data needed to compute them is shown in a tabular view underneath. So if we select this red point from 2018, then two records are shown with these three fields highlighted. So this doesn't provide a full explanation of the selected element, but it does make the connection to data more explicit. For example, we can see that the data from China and USA are being selected, and that can certainly help us understand what we're looking at. And if we now grow this selection to include this green point from 2017, two additional records are shown with the same fields highlighted and so on, if we select a point from 2060. So this relation is monotonic. The more we select, the more data becomes relevant. So something interesting happens if we select a point from 2015. Two of the bars on the left are highlighted. Now intuitively, this is because the two bars on the left consume some of the data needed for the selection on the right. In other words, the bars are selected because they're competing in some sense for resources with the selected points. So this points to a relationship between the two charts. And at this point, we might decide to play the game in the other direction and make the left-hand chart the primary visualization. So if we select China on the left here, the data needed for that bar are shown underneath as before, and now we can see that all the points related to 2015 are highlighted on the right. So these are the visual elements that are competing for the data being demanded by the bar on the left. So one important thing to show here is that this notion of needed data preserves unions. So for example, if I select the data needed for USA, I'll see, again, a data selection underneath. And if I then combine those two selections, so I have both China and USA selected, then the needed data is the union of the data needed by the two selections independently. And this is an intuitive property, but it will also turn out to be an important mathematical property. All right, so that's the feature that's sometimes called brushing and linking, but existing implementations are ad hoc. And what we'd like to do is do this for general purpose programming languages, and also to do it in this kind of data transparent way, where there's always an account in terms of the underlying data that explains why two particular visual selections are linked. Okay, so in the second demo, we're interacting with an implementation of matrix convolution. So matrix convolution is a common algorithm used in image processing. And the idea is to transform an input matrix using a small matrix called a filter or a kernel to apply effects like blurring. So here, if we select a cell in the output, which is this matrix on the right, then the relevant cells in the input matrix and the filter are automatically selected. For example, here we can see that there are parts of the input that are being ignored, and we might also start to surmise with some experimentation that these cells in the input in particular are being ignored because of the presence of zeros in the filter. And if we continue further, we start to see that because this implementation crops the input at its boundary, this affects how the filter is being consumed. So here, the top row, the filter becomes irrelevant when we get here because the image is behaving as if it were padded with zeros. So this demo also illustrates an important round-tripping property. If we select this output cell over here, then this output cell in this corner cell in the output is also selected. And we can see the reason for that if we just select 5 on its own. So then what we'll see is that the resources required for 5 are actually included in the resources needed for 1. So if we demand this output here, we end up getting this output for 3. And there are clearly some UI choices that we could make to improve this. For example, it probably makes sense to show the induced selection in a paler shade of green to distinguish it from the explicit selection. So our conjecture is that this kind of interactivity can help someone understand how an algorithm works. For example, we can contrast the implementation of convolution at the top with another one which wraps at the boundary instead of padding with 0. And that implementation has a nice visual behavior which helps distinguish these two choices. Rather than parts of the filter becoming irrelevant, other parts of the image are consumed. And finally, we talked about unions, preservation of unions and monotonicity in the previous example. We can see that here as well. So this is a view of the computation that's still extensional rather than intentional, but it's fine-grained enough to tell us something about what's going on inside the computation. And the key point here is that we want to enable this kind of interactivity and transparency without the programmer having to implement this feature themselves. The programmer just implements matrix convolution, and the runtime of the programming language automatically enriches the output with the affordances necessary for exploring these input-output relationships. And we have our own functional programming language called Fluid, which does exactly that. And here, matrix convolution is just expressed as a pure function, and there's no logic relating to interaction or anything like that. And similarly, with the linked charts example, the programmer simply creates 2 views of the same data, perhaps in a notebook-like environment. They express the views using standard functional programming features like higher order functions and list comprehensions, and the language runtime takes care of tracking dependencies and linking selections between inputs and outputs. Okay, so let's review the problem we've set ourselves. So we want a way of, first of all, selecting parts of structured values, such as a bar in a bar chart. And we then need a procedure for deriving related selections upstream and downstream, crucially in a way that round trips. So what round tripping is going to mean, or at least one of the round tripping properties, is that if we compute an input selection for a particular output selection, then we want to know that we've selected enough input to be able to reproduce the output selection. So this is what I'm calling sufficiency here. So we can think of this idea of sufficiency as a fine-grained notion of reproducibility. So for this part of the problem, we're building on prior work on Galois slicing, which has this kind of round tripping property. However, the prior work doesn't provide a way to select within a structured value in the kind of way that we need here. Also, we want a way of linking selections across 2 outputs computed from the same input. So let's suppose we have a solution to this problem. Naively, we might be tempted to reuse this solution over here to solve the other side of the problem. However, this sufficiency relation, which I've argued is the appropriate notion over here, isn't directly able to solve the problem on the right. What we want to do on the right is identify the parts of the other output that consume any of the selected input. In other words, for which any of the selected input is necessary. So the problem is that sufficient for relation is in some sense the wrong modality to do what we want. Okay, so I'll turn to the relation that we do need in a moment, but first let's consider the mathematical basis for this round tripping intuition that I've been talking about. So suppose we have partial orders O and I, which are going to stand for output and input, and suppose we have a pair of monotonic functions that map between these 2 partial orders. 2 such functions form what's called a Galois connection if they round trip in the following way. First of all, if I start with an output and determine the needed inputs, then that input better be sufficient for the selected output. In other words, if we round trip in this direction, we go up in the order. On the other hand, if we start with an input and determine the output it suffices for, then that output better require less input than we started with. In other words, if we round trip in this direction, we go down in the order. And we can think of this in terms of lazy evaluation. Not all of the input of the selected input is needed, and the unneeded part is discarded when we round trip. So these two components of the Galois connection, which is written using this sort of backward turn style, are called the lower joint and the upper joint. And each is the closest approximation that there is to an inverse of the other, one from above and one from below. Okay, so Galois connections compose component-wise, so it's useful to think of them as having a direction or a type. So somewhat arbitrarily, we're going to say that the type of the Galois connection is the type of the lower joint. So in this case, it goes from O to I. And finally, the lower joint has an important property, namely that it preserves joins, which we can think of as unions. So if two output selections require X and Y independently, their union requires the union of X and Y. And the upper joint has the dual property, it preserves meets or intersections. And I'm going to use the convention that green means join preserving and purple means meet preserving. All right, so this is the basic framework that we're working within. And let's see now how we can concretely represent selections. So the idea is to annotate every path in a value with a selection state alpha. The most basic case is when the selection state is a single bit indicating whether the path is included in the selection. But it's useful to allow alpha to be chosen from other lattices. For example, we can use a vector of bits to represent multiple selections simultaneously. So using this Boolean lattice, we can represent the bar chart selection as this data structure, which is a list of records where the Y field of one of the records is tagged with true or top, and all the other fields of the remaining records are tagged with bottom. Now, it's useful to distinguish values with this kind of selection information from values with no selection information attached, which we'll call raw values. And I'm going to write an underscore under meta variables that refer to raw values. Then we can define a function called shape, which takes a value with selection information of type A and erases the selection information, producing the corresponding raw value, where the type of the annotations is the unit lattice. And then for a given raw value, underscore V, we can define the selections of that raw value to be the set of value selections which have that raw value as their shape. And then using this notion of selection, we can define a pair of analyses for a fixed program, mapping between selections on its output and selections on the program and its input. And in the forward direction, those selections are going to represent available resources. Going backwards, they represent resources that are being demanded. And going forwards and backwards through the computation is supported by a proof or a trace that witnesses the fact that E evaluates to V. So the details of this analysis are in the paper. What's more interesting here is how we've given this kind of analysis, how we can also use it to link selections between two outputs computed from the same input. Bearing in mind our observation earlier that the sufficiency relation is not the appropriate analysis here. It turns out that we can use the sufficient for relation after all if we generalize the type of selection states from lattices to Boolean algebras. So suppose we have this bar chart selected on the left, which we said we could represent using this annotated value. Under the backwards analysis, that induces the input selection we saw earlier, which we can represent in a similar way. There's some missing records here, I've just shown them before. Now we can negate the selection by applying negation pointwise. The selection now consists of everything apart from the resources needed for the selected bar. If we feed that into the sufficient for relation, we can calculate all the output parts that don't compete for resources with the selected bar. And finally, we can negate again to determine the output parts that do compete with the selected bar for resources. And that has the visual representation that we saw earlier. So what this achieves is turning an analysis that determines what we can compute given a set of input resources into an analysis that tells us what we can't compute because certain resources are unavailable. And this is an example of a De Morgan dual. So any function f between Boolean algebras has a De Morgan dual that negates its input, feeds it into f, and then negates the result. And the important observation here is that if f preserves meets, then the dual of f preserves joins, and vice versa. And in particular, if f and g form a Galois connection from A to B, then the dual of g and the dual of f form a Galois connection going in the other direction. So although the De Morgan dual is covariant at the level of functions, it's contravariant at the level of Galois connections. And this contravariance is key to solving the brushing and linking problem in a mathematically sound way. And we can understand our earlier intuition about sufficiency somehow being the wrong modality to link two outputs in terms of compositionality. So if U and V are two views of some common data, and we have Galois connections capturing their I/O relationships, we can't naively compose these two Galois connections, because that would require composing a join-preserving operation with a meet-preserving one. And the result would, in general, preserve neither meets nor joins. But if we dualize one of the Galois connections, then we can compose them into a larger Galois connection relating U and V. And this formally is the kind of what we informally described as necessity earlier. It's just the dual of the sufficient for relation. Okay, so that's all I'm going to talk about today. The kind of broadest motivation, I guess, is the question of how we can improve on this setup, where we have monolithic input, we feed it into an execution that we run once to obtain monolithic and ultimately opaque output. And I think there are lots of ways we can improve on this picture. But one concrete way that we've investigated in this work is to think of the interesting bit in the middle, not as something we throw away, but as a persistent relationship that the user can explore in fine-grained ways. So you can find out more at these URLs. These are a couple of things that we've been working on, which I'm happy to talk about. And thank you for listening.